discussing about two-port network synthesis. In case of a two-port, you have various specifications. You may have for a two-port network Y11, Y12, Y22, these are the parameters, or maybe A, B, C, D, or Z parameters, and so on. These are the three commonly used sets. Sometimes you may be given only a gain function G12, which is given by this, or minus Y12 by Y22. So, if this voltage by this voltage, this is the gain function, only the gain function is given, then you are asked to realize a network to give that particular gain function. Alright. So, the specifications can be many types, unlike a one port network where you are given either ZS or YS. YS is just inverse of ZS. So, you have one specification. Here the specifications can be in terms of say Y11 and Y12, or Y22 and Y12, any two can be given, or maybe just the gain function. Alright. So, how to realize a network to meet these specifications. So, before we go into that, we will just see the network functions, how they are related to these two port parameters, network elements. Let us take a T network, okay, or a pi network. From a T you can always find a pi. This is a star to delta or delta to star conversion. All right. Normally, if you are given the specifications in terms of Z parameters, you go for an equivalent T. This is easier. Similarly, for Y parameters, we go for pi network. Suppose this is given as YA, YB and YC. Let us take this first. What is Y11? YA plus YC, very good. Y22, YB plus YC, and Y12, okay, minus Y12 is YC. Okay. Now, these elements YA, YB, YC, they can be any RLC combinations. Okay. Let us see Y11. What are the poles of Y11? The poles associated with YA and with YC will be the poles of Y11. Similarly, poles of Y22 will be the poles of YB and YC. So, YC is the common element for the poles of Y11 and Y22, and also minus Y12. So, the common poles in these three will be the poles of YC. So, in Y11 there can be some poles of YA which are not included in the other two functions. All right. So, poles of YA will be present only in Y11, nowhere else. Similarly, poles of YB will be present only in Y22. So, I can remove these poles, still have such poles can be realized as separate elements I am not given YA and YC, YB, YC separately. I am given Y11, Y22 and Y12. So, out of which I find out the poles which are not present in Y12, but present in Y11. Similarly, the poles which are present in Y22 not in y12, I call them private poles of the two ports, private poles of 1 1 dashed and 2 2 dashed. Okay. Poles of y11 and y22 which are not present in y12. Okay. So, the poles which are present in y12 will be present in y11 and y22, but the converse is not true. Okay. So, if I have a network which is having y11 dashed, y22 dashed and y12 dashed as the parameters, then y11 as seen from this side will be y11 dashed plus ya. Any addition of an admittance here will be adding to this value only, is it not? If I have another element, another additional admittance here, that will be changing only y11, that will not be affecting these two, is it not, because it is only ya which is getting modified. So, y11 will be this additional element plus whatever is a y11 dashed here. Similarly, y22 will be y22 dashed plus yb, but y12 will be y12 dashed, is it not, that remains unaffected. Similarly, for the z elements, z11 will be, suppose this I call as z1, z2 and say z3. Then z11 will be z1 plus z3, z22 will be z2 plus z3 and z12 is z3. So, here also you see the poles of z3, that is z12, poles of z12 will be present in z11 and z22, but the converse is not true. z11 and z22 will have additional poles coming out of z1 and z2. Okay. So, if I have a series addition of such elements, this is some z1, z2. Suppose this is having z11 dashed, z22 dashed and z12 dashed, then overall z11 from this side, I should write small z as per our convention, z11 will be z1 plus z11 dashed, is that okay? Similarly, z22 will be z2 plus z22 dashed, but z12 remains unchanged. Okay. So, once again the private poles of an impedance set can be removed as series elements in the respective sides. Okay. So, this is the series and shunt separation of private poles. Now, let us see what are the requirements for the impedance functions, all right, what are the requirements for impedance functions to be realizable. Now, let us take say y11, y12 and y22. So, once again equivalent network. Now, what will be y11? Ya plus yc. If this is ya, yc and yb. Y22 is yp plus yc, and y12 minus y12 is yc. Okay. So, y11 ya minus y12, is that all right? Or ya you can write as y11 plus y12. Okay. Similarly, yb will be y22 plus y12, and yc is minus y12. Now, given any network, you can have a very complex structure of a two-port network. And so on. All right, there can be bridge elements also. Whatever be the type, I can always reduce by repeated star delta conversion. This entire set to either a T or a pi. Is it not? Now, in this repeated star delta conversions, what are the elements? How do you calculate the elements of a star delta set? Say in terms of impedances, Z1 Z2 plus Z2 Z3 plus Z3 Z1 divided by something, all right, divided by Z1 or Z2 or Z3. The operations are all positive, there is no subtraction. Okay. Now, Z1, Z2, Z3, these will be R plus Ls plus 1 upon Sc or their parallel combinations, series combinations. So, they are all having positive signs, and these after multiplication also the signs do not change. Then again you are having additions. So, all the elements will be finally added, there is no subtraction, there is no chance of a negative sign. Is that all right? So, all these elements finally Zs or Ys elements here, that is Ya, Yb, Yc or Za, Zb, Zc, these will be having the forms some A0 s to the power A0 plus say A1s plus A2s square and so on, divided by say An s to the power n divided by B0 plus B1s and so on, say Bm s to the power m. Okay. These elements Ya, these will be all positive real functions so far as Ya, Yb and Yc are concerned. These three elements are positive real. After all, they are obtained after reduction of some positive real functions, star delta reductions. So, this will be having expressions like this. Similarly, Y12 minus Y12 will be Yc. So, Y11 sorry Ya, Yb and Yc are all having positive coefficients of polynomials in the numerator and denominator. So, let us see Y11. What was our Y11? Ya minus Y12. Okay. So, suppose you are given minus Y12 as A0 sorry there was a small slip. There was a small slip. Check. Y11 is Ya plus Yc. Okay. Y22 is Yb plus Yc. All right, and Y12 minus Y12 is Yc. Okay. Therefore, Y11 it may be given, let us write the denominator may be some polynomial, numerator can be any polynomial, that will be a common polynomial if there is no private poles. Okay, we can consider a common polynomial for the denominator. Then this can be say a0 plus a1s plus a2s square and so on. Y22 is b0 plus b1s plus b2s square and so on, and y12 is c0 plus c1s and so on. Okay. So, one of the conditions is a0, a1, this must be greater than equal to 0, that is what we have seen, all of them should be positive. Similarly, b0, b1 must be greater than equal to 0, c0, c1 etc. must be greater than equal to 0. All right. What is y11 plus y12? Ya, is it not? Y11 plus y12 is Ya. Is it all right? Now, Ya has to be with all positive coefficients. So, if I substitute here y11 plus y12 means a0 minus c0, a1 minus c1, all right, into s. So, that gives me a0 minus c0 must be greater than equal to 0, a1 minus c1 must be greater than equal to 0, a2 minus c2 must be greater than equal to 0 and so on. Okay. Similarly, by the same logic, y22 plus y12 is how much? Yb, and that also we discussed after repeated reductions. Ya, Yb, Yc must have all positive coefficients in the numerator. So, y22 plus y12 also must be having numerator coefficients as 0. So, b1 minus c1 is greater than 0, b0 minus c0 is greater than 0, greater than equal to 0 and so on. All right. So, these are the coefficient conditions to be satisfied when you are given the specifications. Is that all right? So, y11 suppose is given 2s plus 5 divided by some denominator, y22 is given s plus 2 divided by same denominator, and y12 minus y12 is given s plus 7 by the same denominator. Is it possible to realize this? No. Let us see y11 and y12, the coefficients, first coefficient 5 minus 7 is negative, so it is not possible. All right. So, this must be less than 2. If it is s plus 1, yes, it is possible. Suppose it is 2s plus 1, then this is all right, but this is not satisfied. Okay. So, if you are having the coefficients of the numerator given like this, the polynomials are given, then by applying this rule you can check whether it is realizable or not, alright, whether the network can be realized. So, this is known as Fialko-Gust condition. So, before going for any synthesis, we must see that these coefficient conditions are satisfied. There are two ways of realizing a two-port network. One is a ladder synthesis, that is, you try to go for realizing zeros of transmission in steps from one end, or there is another one, lattice synthesis, which we will be taking up later on. That is a very interesting synthesis. It is a structure like this. Okay. If you want, you can have repeated blocks of this. So, this is a lattice network. You have ZA, ZB, ZB, ZA. It is like a bridge basically. So, ZA, ZB, and you take the output from here. This is 1 1 dashed and 2 2 dashed, the same as 1 1 dashed, 2 2 dashed. Okay. We shall see what are the zeros of transmission and how to realize them. Okay. Whenever you are having a zero somewhere, what do you mean by zeros of transmission? Transmission zeros means what? I give a signal, at the other end nothing is received, is it not? Now, in how many ways that can be ensured? I give a signal, you take a water pipeline, all right. In what are the different possible ways the say delivery of water at the other end can be disrupted?
So there is a big leak in the pipe.
Very good, there is a leakage. So, water is grounded, basically the pipe is grounded, the entire pressure is grounded. Is there any other way of blocking? So, if you have some blockade in the series path or a short circuit in the shunt path, then you have a zeros of transmission. That means, how do you create a zero of transmission? By short circuiting. At some frequency, suppose at some frequency I find s squared plus 9 in the numerator, that means at s equal to j3 this s squared plus 9 will be vanishing, that is a 0 at that particular frequency. So, at that frequency I want there should be no transmission of signal, and I want short circuit at that particular frequency. No, a short circuit means what? It should be a series resonance. If I have a series resonance at s equal to j3 and that element is put in shunt, okay. So, you are having an element like this, there are many such elements. In the ladder I create this element is say an LC combination. Suppose this is resonating at omega equal to 3, then a squared plus 9 will be giving me omega equal to 3. This is the resonating frequency. This will be the numerator. Okay. So, in Z12, if I have a numerator of this kind, a squared plus 9, my target will be to create a 0 in the shunt element such that the elements are having a resonance frequency at omega equal to 3. Is that all right? Or alternatively, I open any of these, that means there is no transmission after this. So, how do I create that? How do I create that? At omega equal to 3? How do you create that? Parallel resonance, anti-resonance. So, if I have an anti-resonance element, any of these at that frequency, and then there are others, then also it can be blocked. So, a 0 of transmission can be created. 0 of transmission means because G12 is Z12 by Z11. So, it is the 0 of this which will be the 0 of this transfer function. Okay. So, output will be 0 at that frequency. So, that can be created either by a parallel resonance here or a series resonance here in the shunt element. Is that okay? So, you keep on repeatedly removing all the zeros by adjusting these elements. Okay. So, this is the technique of two port synthesis. When you are given the transmission zeros, you convert them into poles and then try to realize a pole. Any 0 can be realized in terms of a pole, is it not? How do you do that? Suppose you are given Z12. How do you remove that? How do I remove a pole, a 0? You take inverse of that function. If it is in the admittance form, then you convert it into impedance and then make a partial fraction corresponding to that pole, remove that. Okay. Let us take, before we go further, let us take a function Zs equal to, say, any function you tell me, say 2 into s into s squared plus 4 by s squared plus 1. Okay. I can make partial fractions k1 s by s squared plus 1 plus k2 into s. Okay. K1 comes out as, if I multiply by s square plus 1 divide by s and make s square plus 1 equal to 0. So, it will be 3 into 2 6 s by s squared plus 1 plus k2 into s. How much is k2? 2 into s, all right. So, that means 2 Henry how much is this? 1 by 6 farad and 6 Henry. Okay. Now, if I remove 2s from here, if I remove this k2 totally, if I remove 2s, whatever is left over will contain only the other pole, all right. If I remove this, I am left with only 2s. Now, in this, the zeros are at 2, 1 and this is a pole. This is a pole 0 configuration, 0, then pole at 1, 0 at 2 and pole at infinity. Okay. Now, suppose in this when I remove this, I remove the pole at this one, what I am left with? Only 2s, a 0 here and a pole here. Okay. For this function, if I remove this, what will be the pole 0 configuration for 2s? 0 here and a pole here at infinity. If I remove this 2s, then 0 here, pole at 1 and a 0 here. Okay. So, if I remove this pole totally, this 0 also gets eliminated, all right. If I remove if I remove this pole, okay, means this is having a pole at infinity, is it not? If I remove the pole at infinity, then infinity becomes a 0 and this pole remains. Where is this pole? So, this pole remains at 1, but the other pole has created a 0 here. Okay. Now, if I do not remove the poles or the poles of either this or that totally, if I retain some part of it, what happens? That means instead of 6s plus a square plus 1, suppose I take 3s by a square plus 1. Okay. Then I call that balance admittance as z dash s as 3s by a square plus 1 plus 2s, okay, and some z removed s is 3s by a square plus 1. That means 50% I have removed, 50% I have retained. So, if I remove 50% of this, means what? 3s by a square plus 1 means I will have 3 Henry and 1/3 farad. Suppose I take out an element like this, whatever is left over is z dash s, is it not? What is z dash s? What will be the poles and zeros of this? Poles will remain same. I have not disturbed the pole. What about zeros? Now, this is not totally removed, it will have a new 0, all right. What I have done is, I have not totally removed this pole, I have weakened the pole, I have removed a part of that residue. Residue was 6s, all right. So, I have taken a part of it. So, if I remove a part of that pole, that is called part removal of the pole, then what do I get in the overall distribution of poles and zeros? Poles remain as they were, but what about zeros? So, this will be 3s plus 2s cubed plus 2s, all right. That means divided by a square plus 1, that means 2s cubed plus 5s in the numerator. So, s into, if I take 2s common, then s squared plus 5 by 2, correct me if I am wrong. Okay. So, the new distribution of pole and poles and zeros will be 0 at the origin is remaining intact, all right. Pole at 1 is again appearing because I have not removed it completely. What about this 0? This 0, it is now root over of 5 by 2. It has earlier it was at 2, now it has drifted towards this. Pole at infinity, that also remains as it is. Okay. So, this 0 at 2 has now shifted to root over of 5 by 2, okay, approximately 1.58. Okay. So, if I weaken a pole, I can shift a 0 to a desired position. I have taken out only 50% of this 6s, this residue. I could have taken any percentage, and hence I could have shifted this to a desired location. Is it all right? Therefore, by partial removal of a pole, I can create a 0 at a desired position. Some of the zeros can be shifted. Had there been many other floating zeros, means between 0 and infinity, had there been some more zeros, they would have all drifted towards the pole. All right. The drift will be by different amounts. All right. I am not bothered about the drift of all the zeros. I may be concentrating on one 0, especially the nearest one, the one which is nearest to this, preferably, to locate it in a new position. And this is not the only pole, there could have been other poles, and my desire would have been to shift this to this side, then I would have weakened this one. Is it all right? So, it all depends on what is the 0 wanted. That means, in Z12, in the transmission, I am creating artificial zeros, all right, by removing the poles partly. This is known as partial removal of poles and shifting of zeros. Okay. So, you can weaken either the pole corresponding to this or this, that means you weaken the pole here, that also you could have seen. Let us see now, instead of 2s, if I take s, what happens? I remove only 1 Henry inductor and rest of it I retain. Now, here I have created a 0 in Z1 dashed s, which is at root 5 by 2. So, this element is having a 0. Let me complete this, then we will go to partial removal of this pole at infinity. So, I have got a network like this, and then z dashed s is a function which is having a 0 at s square plus, that is at root 5 by 2, it is having a 0. How do I realize this? Any 0 you convert it to a pole. So, I will correspondingly I will take y dashed s, which will be giving me s square plus 5 by 2 in the denominator. Okay. There are other factors, okay, and this one I will write as k1s by s square plus 5 by 2 plus other factors. That means, y dashed, the admittance is taken as some y1, y2, y3. So, this entire z dashed which was appearing here is now taken as some y1, which will be corresponding to this, all right. That means, it will be having, this is an LC series element, is it not? If y corresponds to ks by s square plus omega square, that will give you a series LC element, okay. And then rest of it I will again switch over to ZS. I am not bothered about this part, I am interested only in removing that 0. So, convert it to a pole, that is go to an admittance function, then realize that, and then again the balance you again invert, you will get rest of the elements. One by one you take out the zeros in the shunt elements, okay. So, this will be resonating at root 5 by 2. So, that will be creating the 0, all right. By partially removing the pole, we can realize this. Let us see if we partially remove the pole at infinity, that is, let us take again 50% removal, just take S. So, we have got 1 Henry, that is Z dashed S now is S plus 6s by s squared plus 1, and Z removed is just S. Okay. Now, what is z dash s? S cubed plus s plus 6s. So, s cubed plus 6s divided by s square plus 1, oh sorry 7s. So, s into s square plus 7 by s square plus 1. Now, what will be the pole 0 location? Earlier it was a pole, sorry, a 0, a pole, a 0 and a pole. Now, I have weakened this. So, under the new situation z dash s, this was for zs, z dash s is having 0 once again at the same point, pole at the same point, this pole is also at infinity, but here it is, earlier it was 2, now it is root 7, now it has drifted to this side. So, 0 here has drifted towards this pole which has been weakened. So, wherever you are weakening the pole, the zeros will drift towards that. Okay. Earlier it was in the other side, so the 0 drifted to that side. So, depending on the 0 that is given in the transmission, this is corresponding to the transmission 0. So, the zeros of transmission, where they are located and what is given in Z11, if you know that Z11 is at 2 and the zeros required 0 of transmission is at root 7, then I will be weakening this pole first, so that this drifts here. Alright. If I weaken this pole, then it will be drifting to this side, I cannot realize a 0 here. Alright. So, this is the technique that we follow for ladder development. And we want a 0 at that particular frequency. So, what should be the value of that residue, that is we have seen only 50% removal, what should be the percentage removal, what should be the percentage removal of the residue, so that we can get the desired location of the 0. Okay. So, that is the next question. Let us take up an example, it will be clear. Say Z11 S is given as s squared plus 9 into s squared plus 25 divided by s into s squared plus 16. Okay. Let us make a plot of these poles and zeros first and then decide about the shifts. So, there are no private poles, Z12 and Z11 are having the same poles, alright. If there are private poles, remove that first. So, poles and zeros are for Z11, is the origin a 0? Pole. Then 3, 4, okay, they are not to the scale anyway, 5 and then at infinity there is a pole, this is Z11. Z22, Z12 pole, poles are same because there is no private pole. So, the poles are identical and then this one is at 1 and then this is at 2. Now, in the transfer admittance or transfer impedance, there is no hard and fast rule that poles and zeros should alternate. Transfer admittances Z12, how much is Z12 in terms of Z1, Z2? There need not be Okay, we will discuss about it later on. See, the poles and zeros need not come alternately. So, they need not be positive real functions, they need not be positive real functions. Is that clear? Any question? They need not be positive real functions. How fallacious. Z12 by repeated star delta conversions, you got Z12 as this impedance, but this need not be a positive real function. This need not be a positive real function. Only thing is the numerator and denominator coefficients must be always positive. When you go for repeated star delta conversions, you must get all the coefficients as positive, but repeated conversion of star and delta, that need not guarantee positive real functions as elements. That means the element may not be realizable. Element may not be realizable. For example, you are having an inductor, a capacitor, an inductor, a resistor, and so on. If I reduce it to a star or a delta, this may give you some ZS, it may not be realizable. It will be having a function, all right, with all positive coefficients A1s, A2s squared and so on divided by B1s, B2 square, but it may not be a positive real function. You may not be able to realize it by RLC. Okay. This is a very interesting point. So, this is very clear from Z12 itself here. A squared plus 1 into a squared plus 4 by S into a squared plus 16. So, you can see the zeros are coming consecutively, I mean 2 consecutive zeros and then a pole comes. So, what should I do? I can shift this 3. So, these are the values 1, 2, 4 and 5. Either I can shift this 0 here or this 0 here. So, either you can weaken this or weaken this, is it not? So, if you want to shift this here, you have to weaken this, that means a part of this residue has to be removed. Okay. So, Z11s, let us break up. Z11s, if you write as K1s plus K2s by S squared plus 16 plus K3 by S. I am not really concerned about all these, I am interested only in a partial removal of this. Suppose I write this as sum K1 dashed S plus Z11 dashed S. That means this is the part removed, this is a part removed and this is what is remaining, all right. Now, Z11S, so Z11 either at j equal to omega equal to 1, that is S equal to J1, or S at J2, this will be vanishing, all right. Sorry, the impedance at that point, impedance at that point J1 or impedance at J2, I want this to be 0 for Z12. For Z12 this will be equal to 0, is it not? So, Z11 dashed at J1, if I take it as 1 because I am shifting it here, should be equal to 0 is it not? This must be 0. So, what is this? If I put on this side, Z11 at J1 should be equal to K1 dashed into S equal to J1. So, how much is K1 dashed? Calculate from here. Is it okay? Z11 that was given as S square plus 9 into this thing. So, put S equal to J1. So, that is 9 minus 1 8 into 25 minus 1 into 24 divided by 15 into J, okay, and this J is there already. So, that gives me K1 dashed into J1, all right, K1 dashed into J1. So, calculate this, how much is K1 dash comes out as minus 64. Now, check whether it should be minus Z11 J omega plus K1 dashed into J1 is equal to 8 into 24 divided by S into S squared plus 1 15 . Is that all right? We are trying to make it at 1, it is at 0. So, 1, okay. K1 dashed is, let us see whatever be that value, minus 64 by, no, J into J will be, so it will be plus. Minus 64 by 5. So, that means we will have to add, that seems to be somewhat funny unless we have made some slip. Okay, let us see the other one. I will come back to this. You also think over it, why we should get this, or what we are trying as K2 dashed S by S square plus 16 into some Z11 double dashed S. Either remove this partly, then it will be shifting to 2.
So, 3 is greater than 3, so on weakening 0 only 3 will shift towards 2.
Sorry.
So, on weakening the 0, the pole at 0, 3 will tend towards 2, it will go this side.
Sorry. 3 will be 2. Thank you very much. That is why this scaling was very, very important. So, in any case, you can weaken this to shift it to either 1 or 2. Okay. Thank you. So, in that case, what will be this one? Z11 double dashed at J2 should be equal to 0. This is a 0, which gives me, yes.
We won't weaken the pole at 4, we will weaken the pole at 0.
So, not K2 dash S by S square plus 16.
And when we
K2 dash S.
Sorry, we are weakening the pole at the origin.
Yes, sir. And when we weaken it, the pole at 0 at 3 will tend to 0 at 2.
Yeah,
So, we should write the impedance
J2.
function.
that is what I am putting, J2.
Z11 at J2. Z11 dash at J2.
I am going to write that. That is what I am going to do. This will be
Not K2 dash S.
Z11.
Z11 double dash is by weakening the pole at 4.
Yes.
Okay, let us write it here. Okay, we will continue with this in the next class. The time is over. We will continue with this in the next class. Thank you. Good morning, friends. Last time we were discussing about LC synthesis. We got stuck in a little problem. See, we had Z11S, there was a slip we made. We had something like this, S squared plus 16 plus K3 by S. So, while removing the pole partially, we are concentrating on K1S. Instead of that, it should have been in K3S, okay. And from there you will get the value of K1 dashed corresponding to the one that is to be removed, K3 dashed, okay, and you will get the pole shifted. So, I would leave it to you for completion of this. After that, it is a very straightforward method. We will take up today RC networks, all right. RL is not used so often because of the imperfection in the inductance L. So, RC is a very commonly used network. So, we will concentrate on RC network. Before we go to RC network in details, we would like to see the properties of ZS and YS. Some of the properties of ZS and YS which we did not study earlier. We will see what would be their plot in the S domain. Suppose we consider the ZS function, it may be S plus 2. Let me take a very simple example, S plus 5 divided by S into S plus 4. The pole is at the origin. So, 2, 4, 5. What would be the impedance diagram? Z sigma. If I put S is equal to sigma, that is minus 2, minus 4, minus 5, these are the poles and zeros, and if I put any other value of sigma, what would be the nature of variation at least near these poles and zeros? It will be a pole here passing through 0, this is a pole. So, it will be from infinity passing through 0, it will be going to infinity. Okay. Again from here it will be going like this.